So you have seen this kind of diagram in like organic chemistry. For example, here you have the tin 2 plus reacting with iron 3 plus. Okay, then there must be activation energy involved. Jeffrey, is that a hand? Okay. Okay, now look at this diagram. Now this is the initial energy level. Then this is a product level. Then of course the products better be lower energy than the initial. Otherwise, the reaction will be unstable because this is lower energy, so they are more cool, right? And therefore stable. Now, when you calculate the delta E before and after you combine the two, right, reactants to form the product, then you get the delta E overall. So the delta E overall is represented from this initial to this final. So the plus meaning is going to be spontaneous, right? Plus spontaneous, sure, because this is higher energy, this is lower energy, and with plus, and therefore the reaction is spontaneous. So this is what that means. Now the reaction rate is governed by the activation energy, the amount of activation energy. Now if that energy level is low, for example, in here, low in here, then the reaction is like from here to jump to here, then it's fast. Now, if that is high, then you will need to climb the hill until you reach to that high, then you fall down. Okay? So this activation energy is your limitation for rate of a reaction. Okay? Okay, so but you want to do that, right? Would be ideal if you can predict by looking at an equation to predict whether a reaction is fast or if it's slow. So now it seems that looking at this, there's no prediction possible. So chemistry is experimental science, right? So you just go ahead and do a lot of reactions and measure the kinetics, the rates. You learn in Chem 1B experiment. So measure the rates of reaction, and then because a lot of reactions, then based on the rate, then you can come up with generalizations. Okay, once you get the generalization, then now you can do prediction. Okay, so the prediction is not going to be based on the magnitude of that. Rather, it's based on experimental evidence. Okay? So now here are some examples of experimental results. So you measure the times for 99% of the reaction is finished. So things like that, when mixing serum 4 plus and 2 plus, is fast reaction, take less than a second finish. So if you mix with an anion, so this is the whole deal, is a complex. It's not the Fe itself, rather is an anion, and mixing with that, and the reaction is also fast. And things like that, so on and so forth, So notice, and this one, mixing with that, is slow, 100 seconds, several minutes, a couple of minutes, finish. And then if you react something like this, then it's very, very slow. Okay, then what about you react something like this? Seems to be, just 1 plus difference, but this is extremely slow, then there's only 0.1% finish in 100 seconds, right? So things like that, etc. Then by looking at all the times, reaction rates, then you can make generalizations. Okay, so now, I didn't touch anything. Go on. Okay. turn. Okay, here generalization based on observations. For one, number one, so whatever between a metal ion, so it's cation, between two metal cations, then when the number of electron transfer, one is gained, one is lost, is unequal, then the prediction is slow whenever unequal number. As demonstrated in here, the half reaction, right? So if you look at this guy, then the two electron transfer. Then look at this here, is one electron transfer, right? So based on the half reaction here, then obviously you're seeing uneven number of electron transfer. So the combination between the two for redox reaction is going to be slow. Okay, so this is your prediction. So remember that. Any question?
So
Yeah.
because the first half reaction is losing 2 electrons and the second one is 1 electron, the discrepancy between the two.
That's right. That's right. Yeah. Yeah. So the first one is going to have a 2 electron transfer. Depends on which one is reduced, which one is oxidized. The second one is just 1 electron transfer. So the overall reaction you need to factorize, to the common 2 electron. Nonetheless, simply look at the 2 half reactions. If they involve uneven number, then it's going to be slow.
If it was, say, it was 2 electrons being on the second half reaction, would that mean it was fast then?
That would be fast.
Okay.
Yeah. Okay. Now the second one. The previous one was between 2 metal ions. Here it could be either between 2 metal ions or between a metal and a non-metal ion. Okay, so will be true like that. Okay, here generalization based on the structures of the chemical formula. Okay, if the structures are more complicated, then your prediction will be slow reaction. Okay. So, for example, here, these 2 reactants. Okay, then the products, things like that. So the permanganate into manganese, the structural change is tremendous, right? This is simple, just the manganese itself, but this is associated with oxygen to form the oxide bond. So the energy is going to be required to break this bond before they can form this product. So you have high activation energy right here, right? And here too, this guy is going to break bonds, right? But there's a CC bond in between, then that is a tough bond, need to be broken. So the 2 together combined will have a high energy requirement, okay? So we are only consider the energy requirement here without considering the orientation, But that alone will give you sufficient prediction that this is slow. Okay. And prediction number 3 is between cation and anion. Now this is simply predicted as fast. So as you see the title, as long as you have a cation and an anion, regardless of structure, then it's fast. Then here, sure, this is a simple structure that you can see. One is a cation, one is an anion, because they like each other. So they will simply collide and give off a lot of energy, enough to form the product. So it is a fast reaction. So cation and anion. And what about this? There's a more complicated formula for anion. But then the title is simply cation and anion. This is the anion. It doesn't say it's significant structural difference. Okay, so as long as this is anion, this is cation, they like each other, get that big collision and generate enough energy, and therefore it is a fast reaction. Even though this guy has the oxide bond, just like the previous case. The previous one, they were both anion, right? Actually. So in here, one is cation. So the collision will provide sufficient energy to break that. So it's fast. So this is a tricky generalization. Okay? So memorize that.